This is a pretty small topic that we're going to talk about, this linear approximation idea. I've got a list of things that we're going to do today. First, we're going to introduce this idea of local linearity of functions. It's a really important but kind of obvious feature about our functions once we see it. And so I'm just going to give a nice visual demonstration about what local linearity actually means. Then from that, we'll build this general idea of what linear approximation does. This is an idea that's going to scale really easily. You're going to talk about the same kind of thing in Calc 2, super applicable. And we'll do a couple of examples of that, and then we'll try and figure out how good is our approximation, how do we know, how can we tell anything about our approximations? Because we are going to be doing a little bit of educated guesswork here. All right, so let's get this started. Let's jump into this idea of local linearity. So I got a couple pictures of graphs to show you. Local linearity is a property of what I'm going to call a nice function, and we'll talk about what that really means. So what I've got is a picture of a function. We'll call it f, whatever, doesn't really matter. It's got a point on that function, and it has a tangent line at that point. Cool. What we're going to do is we're going to zoom in on the blue circle there. So I'm going to skip forward. Same picture of our graph, but we're zoomed in now. I've got a new blue circle, right? So I'm going to zoom in even further on that blue circle. And so this picture that we have is what was in the circle before. And I'm going to zoom in one more time. And what you're noticing is that when we zoom in really far, our function looks like a straight line. You can tell that because doesn't our black function kind of match up with the red tangent line here? We'll go back and see how this works again. Okay, so right now, this function is clearly not linear. I picked a point at a spot that's relatively curvy. I could have picked a point right here, and it looks like that's pretty linear. That looks almost like an inflection point, right? Maybe the concavity is close to 0 here. So I picked a point with a decent amount of concavity, some curvature. And when we zoom in, we can still see that curvature, but if we look in the blue circle, it's not as curvy. And again, when we look in there, it gets flatter and flatter and flatter as we zoom in further and further and further. So this is what local linearity means. In a small, localized area around a point, that's what I'm representing with these little circles here, these little kind of neighborhoods around a point, every function is close to linear. Now, really not every function. Every nice function is close to linear. And what I'm going to say here is that what nice means is continuous and differentiable. No sharp corners or anything like that. No discontinuities or anything like that. As long as we can draw tangent lines, we've got continuity around this point that we're looking at, we should be good to go. Local linearity is not that big of an idea. If you zoom in far enough, every nice function looks like a straight line if you zoom in close enough to it. Cool. All right, so what we're going to do is take this little idea and build it up to a really nice, kind of cute result that we're going to have. This is called linear approximation, and as you can imagine, we're going to be approximating things using a straight line. So here's the main idea. For a function f that is nice, continuous and differentiable at some point x equals a, we'll call it, the line that is tangent to f at a approximates the function f of x for x values close to a. Okay, that's kind of a big, long sentence, but let's unpack this. What this means is exactly what we just saw. Tangent lines and functions act the same when you get really, really, really close in to a point. If you zoom in really far, if you look at a really, really, really small little local neighborhood around a point, the function is essentially linear, and so the tangent line and the function are pretty much the same thing. So that's what we're looking at here. The function and the tangent line seem to act really similar when we zoom in on the point at x equals a. The closer we get to that point, the better job the tangent line does. Let's go back and just see that. Hey, doesn't the function and the tangent line look almost identical here? When we get a little further out, though, our function seems to be riding close to the tangent line, right? It hasn't curved away yet too much, but it's not perfect, right? This function and tangent line aren't matching up exactly. And the further away we zoom, the more complications we could have. All right, now when we go all the way back out to our original view of our function, the function and the tangent line look like they're acting completely differently. But again, zoom in really close, They're almost identical to each other. You can see there's a tiny bit of deviation right around here, right on the ends. You can see that black line is separating from the tangent line a bit because that curvature is starting to take over, but it's not too bad. So that's what we've got. This is how we can express that in notation. We're going to use L of x as our linear approximation. And what you'll notice is that this is just the tangent line, right? That's the slope of the function. That's the x value. And that's the y value. So this linear approximation function that we've built is really just the equation of a tangent line. We've done that part before. We know we need an x value and a slope and a y value. We get the slope from the derivative. We get the y value from the function, blah, blah, blah. Put it all together. And the whole point is this. These two things are approximately equal to each other. This little squiggly equals sign means approximately the same thing, like almost equal. For x values close to a. Now notice we are not formally defining what close means. So we're going to have to investigate that a little bit more too. So if we build a tangent line, it's going to do a fine job approximating y values. If we go back to this picture that we have, I'll draw a y value or a point maybe on the black line right here, and I'll draw a point on the tangent line right here, and we can see that they are almost the same thing, right? A little bit further away, maybe that point on the line and point on the tangent line are close to each other, right? The y values are close, but not really that close. Here, it's like they're kind of stepping on each other. The coordinates of these points are almost identical when we zoom in really, really far. So that's what we're saying here. L of x, the y value of the tangent line, is approximately equal to f of x, the y value of the function, for an x value that's close to this point at which we built the tangent line. So when you get really, really, really close to that intersection point between them, the y values are going to almost be the same. All right, let's take a look at some actual examples where we do this. I'm going to probably leave some of these open for you to just play with. Maybe I'll fill them in. I don't really know. I'll keep an eye on the time of this video, make sure it doesn't get too long. This is what we're going to do in general. We're going to be given some value that we want to approximate. It's going to be some function output. I'll call it f of x sub 0, or x naught, sometimes we call that. If you want to see how to spell that, that would be, we might read it as x naught. Zeros and O's are sometimes called naughts in the UK, I think. I don't know. Anyways, in math, that's what we'd read it as. For some general function f of x. The way that we're going to do that is use a linear approximation centered at some value. We'll call it a. That's the point at which we're going to build the tangent line. And we're going to call that some nice value. We'll explain what that means. Near x sub 0. So we have some value that we're looking at. Find an x value that's close to this one and is nice. What do we mean by nice? Well, notice we have to evaluate our derivative at a, and we have to evaluate our function at a. We need to know f prime of a and f of a. So if you have some like crazy function with a derivative or something like that, we'll try and pick an x value that's going to be nice for that. What that means is like consider a trig function. Maybe let's just think about the cosine function. A nice value here might be some sort of an input angle where we actually do know what the cosine of that function or what of that angle is. So maybe like a nice value is 0 or pi over 4 or pi over 6 or 3 pi over 2 or something like that. Looking at cosine of 7 is not super helpful because I have no idea what the cosine of 7 is, right? I don't know what the derivative of the cosine of that is because the derivative of cosine is negative sine. So depending on the types of functions, you're going to have to try and pick centers, these a values, that act well there because we actually have to know what that derivative evaluated at a is. Cool. And then again, L of x is approximately equal to f of x for x values near a, but since we picked a to be pretty close to x sub 0, that means that we can use the linear approximation to approximate this value that we want to know. Okay, let's do it. Hopefully this will become a little bit more concrete, a little bit more understandable. when we actually do it. This is pretty spelled out for us. There's tons of information here. We're going to build a linear approximation of this square root function. We're going to center it at 4. You can imagine why I'm picking the center to be 4 here, to approximate f of 3.5 or the square root of 3.5. So think for a second, why am I picking 4 to be the center of this? Pause the video if you want. I'm going to spoil it in like 5, 6, 7 seconds. I don't know. But think about that. Hopefully you saw that it's because I know what the square root of 4 is. The square root of 4 is 2. And so this x value of 4 is nice since f of 4 and f prime of 4 are easy to evaluate. Also, four is close to 3.5. So with this square root function, I might be thinking about trying to pick perfect squares for my center because I know what the square root of those things are. I'm not going to pick a perfect square like 81 though, because 81 is nowhere near 3.5, even though I know the square root of 81. Similarly, I probably don't want to pick 0. Again, I know the square root is 0. It's 0. That's a nice easy value for this function, but 0 is not that close to 3.5. And so if you think about that picture, we'd be looking at points kind of far away from the center, right? We want to look at points that are close to that center point where we built the tangent line because that's where our function and tangent line are similar to each other. So let's go ahead and build this linear approximation. We need the function. I'm going to call that x to the half or the square root of x. We need the derivative. That should be pretty easy by now. This is 1 over 2 root x. We need to evaluate these things at 4. That's the square root of 4. It's 2. I know what that is. F prime of 4, that's 1 over 2 square root 4. That's 1 over 2 times 2. So that's a fourth. I can build my linear approximation then, because I need a slope, 1/4. I need an x value, 4. And I need a y value, which is f of 4, that's 2. So again, f prime of 4, 4, f of 4. Or you could think f prime of the center x value, and the center y value. Neat. This is a line. It's 1/4 x. If I do the distributive property, I've got minus 1. 4 times a fourth is 1, plus 2. This is 1/4 x plus 1. Okay, cool. What does that do? The whole point here is that L of x is approximately equal to f of x for x values close to 4. And guess what? 3.5 is an x value close to 4. So what this means is 1/4 x plus 1 is approximately equal to the square root of x for x values close to 4. And so that means, oops, not negative a fourth, positive a fourth. 1/4 3.5 plus 1 is approximately equal to the square root of 3.5. I know what a fourth of 3.5 is. 3.5 is 7 halves. So this is 1/4 times 7 halves plus 1. That is 7/8 plus 1. That's 7/8 plus 8/8. So that's 15/8. So what I've just said is that the square root of 3.5 is approximately equal to 15/8. Neat. So you can do this to approximate values that you don't know what they are pretty easily, as long as you can find a center that's going to work out really nicely. All right, so here's my question. Is 4 the best center to use? Is it the perfect square that is closest to 3.5? You might think about that for a half a second and say, yeah, I think so. Because the only other perfect squares that we know would be like 1, and that's far away. It's 2.5 units away from 3.5. 4 is only half a unit away, and then anything bigger than 4 is going to be further away from 3.5, right? And that's true if you're only considering integers, But let's think about this. What if we make 81 over 25 our center? 81 over 25 is like right around 3 1/4, kind of. That's even closer to 3.5. So what we can do is replicate this by saying, all right, we'll use the same function, that square root function. We can look at the square root of 81 over 25. And look at that. This is a value that we can find, 9/5. We'll look at f prime of, oops, I said x. I'll say 81 over 25. We'll look at f prime of 81 over 25, and that's going to be 1 over 2 times the square root of 81 over 25, which is 1 over 2 times 9/5. So that's 1 over 2 times 18/5. That's 5/18. And now we can build our linear approximation. Again, we'll say, all right, L of x is equal to our slope, 5/18 times x minus our center, which is 81/25, plus our y value, which is 9/5. Now, this is a more annoying linear approximation to work with, right? I'm probably going to need a calculator to figure out what 5/18 times 81 over 25 is. Let me think. We can cancel some stuff, right? This is really, let me just do this up here. So that's a 1 and a 5. 9 is a factor here. All right, I got this. So this is 9/10. Negative 9/10 plus 9/5 is going to be negative 9/10 plus 18/10, and so that's positive 9/10. And so our L of x is equal to, maybe I'll put that all the way up here, 5/18 x plus, oops, 9/10. All right, and all of this to say L of x is approximately equal to f of x. And so that means L of 81/25 is approximately, oops, sorry, not 81/25, I'm sorry. L of 3.5, I'm going to call that 7/2, is approximately equal to f of 7/2, and that's our square root of 3.5. L of 7/2, though, is 5/18 times 7/2 minus 9/10. And again, it's some annoying arithmetic to do. That's 35 over 36 minus 9/10. I'd have to find a common denominator here, which is going to stink. I'll probably just use 360 because it's going to be easy to do. This is 350 over 360 minus 9 times 36 is 360 minus 36, so that's 324. So I've got, something might be wrong here, because this is going to be really, really small. Oh, silly me. That's plus. All right, there we go. So this is easier then. This is 674 over 360, which you could reduce and figure out what that is as a nicer fraction, right? That's maybe like 337 over 180. I don't know. All this to say, this is an approximation of the square root of 3.5. So 337 over 180 is approximately equal to the square root of 3.5. So we have two approximations. 15/8, and 337 over 180. Which approximation is better? Hopefully we can tell that this second one is, because our center, 81 over 25, is closer to 3.5. So this is a better approximation, although it's a more annoying one to get, right? This first one was really slick because, whoops, let me get this out of the way. This first one was really slick because we're just evaluating at like easy integer values. And so evaluating that function was really nice. Building the linear function was nice. Here, building the equation of the tangent line kind of sucked. And evaluating that tangent line was a little annoying. Only because dealing with fractions is a little annoying, though. Okay, let's do another example. Notice I'm leaving out some information here. We're going to build a linear approximation of this function natural log of x to approximate the value of natural log of 2. I did not tell you what the center should be. So pause this for a second and think about what's a good center? What's a nice value on the natural log that happens to be close to 2? Go. Okay, hopefully you found that 1 is pretty much the only option that we've got, right? We don't know a lot of values on the natural log function. There's this one right here, though, at 1, 0. And so we'll say, all right, let's use x equals 1 as, the center. So that means we got a function, the natural log of x, and we've got a derivative, 1 over x, and we'll evaluate these at 1. That's the natural log of 1. That's 0. F prime of 1 is 1 over 1. That's 1. So we can build a linear approximation. Our slope is 1. Our x value is 1. Our y value is 0. So x minus 1 is our approximation. So if L of x is approximately equal to f of x for x values close to 1, that means L of 2 is approximately equal to f of 2, meaning 2 minus 1 is approximately equal to the natural log of 2, or 1 is approximately equal to the natural log of 2. You can check that on your calculator, and it's like, okay, it's not great. It's a fine approximation. What we'll notice, though, is that there's not really a nice way of getting a better one, right? It's hard to pick centers on this natural log function because we only know like a couple of values on here. With that square root function, we could kind of tinker with the fraction and find a perfect square that was going to work nicely for us, right? But with this one, we're a little bit stuck. So here, we really can't get that much better of an approximation. All right, last one for you. Try and do this one on your own. Think about what your function is. Think about what a nice center might be. I would say focus on this value. I just rewrote that to show you because 0.001 is really 1 over 100, and so it's a 100th root of e. But focus on this value. Pick a function, pick a center, see if you can build a linear approximation. Go. Hopefully you got something like this. I picked the center to be 0 because I know what e to the 0 is. I really don't know a ton of other powers of e that nicely, but this one's a good one. And heck, 0 is really, really close to 0.01, right? These are right next to each other. So I picked that center to be 0. My function is the exponential function e to the x. That means the derivative is also e to the x. So I can build my linear approximation. It's just x plus 1. And then I know that this x plus 1 function, that linear approximation, the tangent line, is approximately equal to the exponential function for x values close to 0, which 0.01 is close to 0. So what we've got is that 1.01 is approximately equal to this exponential function. Let me draw this really quickly. Whoops, I've got a straight line and I don't want a straight line. There we go. Here's our exponential function. And here's the tangent line. I will use a straight line for this. And what we're doing is we're looking at a point right here, right above 0, right? 0.01. And we're saying these 2 points, the red one and the blue one, are really close to each other. So 1.01 is the y value of the red point, and e to the 0.01 is this unknown y value of the blue point, but we know they're close to each other. So that's what we've got. All right, so the question is, how good are these approximations? We know that probably some of them are pretty good, right? That last one was probably decent. That one with the weird square roots, that was probably okay. The natural log one, probably not that great. How can we tell, though, and how can we get better? So the first main thing is that closer is better. What that means is if your center is close to the unknown value, the x value of the unknown value, at least, then you can get a really, really good approximation. So finding a good center is really important, and sometimes that's difficult. For instance, if we were looking at that natural log function and I was trying to approximate the natural log of 20, I really only know stuff that's close to 1, and 20 is not that close to 1. You can do some tricks with properties of logs to try and simplify things down, but it ends up being really, really difficult still to find good centers for some functions. Another thing that you can do to assess your approximation is to look at the error. Basically, just look at the actual y value minus your linear approximation, and we probably don't care which one's bigger. And if you do, whatever, take the absolute values off. But get rid of the absolute values, or keep the absolute values on if you don't care about which one's bigger. The problem with this is that you actually have to know what this function value is. And if you do know it, then it seems like silly to use a linear approximation. Like if I knew what the square root of 3.5 was, I would have never done that example where I needed to approximate the square root of 3.5. You can look it up on your calculator and stuff if you want, but what really I think is that it's not really worth talking too much about error or percent error here. So, yeah. Sometimes people will call this a weighted error, whatever. What I do want to talk about, though, is if we can tell if our approximations are too big or too small, if they're over approximations or under approximations. And I say concavity is going to help us out here. Let me actually just draw something first. Let's draw something that was kind of like that first function that we were looking at, right? We had this function that was like that, and we picked some sort of a point here, and we said like, okay, we want to find a linear approximation using a tangent line. So let's just think about what our linear approximations are going to be here. Let's pretend that we're kind of far away, so we have a bad approximation, but whatever. We're trying to use the red point to approximate the black one. It's probably pretty clear that the red point is going to be an under approximation of the y value because look at it, it's below, right? The y value is smaller. We can tell from the concavity, though, because if our function is concave up, remember that means that it sits on top of the tangent lines, and that means that your tangent line is going to be underneath the function. And if we use the tangent line to approximate the function, that means in this case, clearly an under approximation. So testing the concavity is really nice. What we'll do to test the concavity is look at f double prime of a, the center. We'll say when we built the tangent line, was our tangent line above our function or below? And really, we're just looking at the sign of this. This is almost like the second derivative test, right? Where you just check the concavity at the point if it's concave up or down. So let's go back to that old example that we had where we said e to the point 0.01 was approximately equal to 1.01. We had this nice function e to the x, and the derivative was, the first derivative was e to the x, and we were looking at a center being 0. We can check the concavity here by doing the second derivative. Hey, look, it's also e to the x. And then evaluate the second derivative at 0. That's 1. That's a positive number, meaning our function is concave up, so the tangent line is underneath the function. What that means is that our linear approximation is an under approximation. So we've got that 1.01, is approximately equal to e to the 0.01. But we also know that 1.01 is too small. Maybe I'll put less than or equal to, just because it could be a case where you have weird functions that are already straight lines, and so they are equal. But if it's a nonlinear function, then it's going to be strictly less than. So now we have a bit more information. Not only is e.01 close to 1.01, but it's a little bigger than 1.01. And again, that's because of this picture of our exponential that we can draw. That exponential function is right there. Here comes our tangent line, and it's underneath, right? And so when we looked at the point on the tangent line, the red one, to try and approximate that blue point, it should be a little bit underneath because of the upwards concavity of that exponential function. That's everything we need to know about linear approximation. Hopefully that's a helpful thing. This gets extended in Calc 2 in a really easy way. The easy way that this can get extended, and you don't need to know this for now, but to just think about in the future is that these tangent lines end up running away from the function, or maybe the functions curve away from the tangent lines. So what if we added some curvature to our lines? What if instead of looking at a tangent line, we looked at something like a tangent parabola? That might do a better job of approximating this exponential because it has some curvature. That might be helpful.